Welcome to the Power Electronics class. Myself B. Virnarayana, Senior Assistant Professor, Department of Electrical and Electronics Engineering. The last class we are discussing the second unit, AC to DC converters, which are called rectifiers. Coming to the unit outcomes, at the end of this lecture, student will be able to explain the operation of single phase full wave rectifier. Coming to this today's module, single phase full wave controlled converter. At the end of this lecture, student will be able to explain the operation of single phase half wave controlled converter with RLE load. Later, learning outcome 2, we are able to explain the operation of single phase full wave controlled converter with R, RL and RLE loads. So first we go through the single phase half wave controlled converter with RLE load. Single phase half wave controlled converter with RLE load. Here RLE means here E is considered as the back EMF of the DC motor. Okay, so here single phase half wave control converter simply consisting single SCR. Here the single SCR is used to convert this alternating voltage source into the DC. Here we have the single phase AC supply, one SCR, and the load. Here the load is the combination of resistive, inductive and the back EMF of the DC motor. For example, if this single phase half wave control converter fed to the separately excited DC motor, then we have some back EMF. That back EMF can be represented by the E. So coming to this operation, this straight line simply represents the back EMF. So if you go through the single phase half wave control converter, we know during the positive half cycle of the supply, anode is made positive and cathode is negative, corresponding that SCR comes to the forward biasing mode. But if you go through this RLE load, especially whenever the source voltage is below the back EMF, then the back EMF dominates the source voltage, corresponding that SCR will be in the reverse biasing mode. Hence why you must ensure that before E greater than source voltage, we are unable to trigger the SCR. Why? Because the SCR will be in the reverse biasing mode. Whenever the voltage across the SCR, the source voltage must be greater than or equal to the back EMF. At that condition only we are able to provide the gate pulse to the SCR, corresponding that it comes to the on state. So what is the minimum instant at which you are able to turn on the SCR? That should be determined here, this theta 1. Here this theta 1 simply represents whenever this Vm sin theta 1 is equals to E, then that minimum firing angle is simply given by theta 1 is equals to sin inverse E by Vm. Here E is the back EMF of the DC motor, which is the known value, and Vm is the maximum source voltage. Once you find out this theta 1 depends upon the load, then we are able to find out the minimum angle at which the SCR comes to the forward biasing mode. After that, if the SCR is in the forward biasing mode, if you provide the gate pulse, then it comes to the on state. Similarly, the maximum instant that we are able to turn on that SCR is simply given by theta 2 is equals to pi minus theta 1. See here, this is the theta 1, which is the minimum firing angle which is able to trigger the SCR, and the maximum instant at which the SCR is in the forward bias is theta 2. Between this theta 1 and theta 2, if you provide the gate pulse, then the SCR comes to the on state. before the theta 1 and beyond the theta 2, SCR will be in the reverse biasing mode. Why? Because the back EMF dominates the source voltage. So anode is made negative and cathode is positive, corresponding that the SCR is in the reverse biasing mode. So here we will take, at this instant we are considering the alpha. That means at this instant we provide the gate pulse to the SCR. We already said after the theta 1, SCR will be in the forward biasing mode. So here at this instant we provide the gate pulse to the SCR. Assume discontinuous conduction mode. So at omega t is equal to alpha, we provide the gate pulse to the SCR, then the SCR comes to the on state. Whenever the SCR will be in the on state, then the source voltage is transmitted to the load through the SCR. Hence the output voltage simply follows this portion of the source voltage. See here, this is the output voltage, and during the process there was some energy must be stored in the inductor. Hence why the current flow through the circuit is like this. At omega t is equal to pi, even though the output voltage is 0, the output current cannot be 0 due to the presence of the inductor. We already said that inductor stores the energy as in the form of electromagnetic field. So after that, after the pi, the energy stored in the inductor is discharges to the source through the SCR. Hence why the discharging current will be like this. Up to the instant where the energy or where the current flow through the inductor is 0, up to that instant the SCR is continuously in the on state. Due to the presence of the inductor, the conduction portion of the SCR is extended up to the instant where the energy stores in the inductor is completely discharges. So due to this conduction period of the thyristor, this small portion of the negative portion will be available across the load like this. So this is the output voltage from alpha to some beta, which is source voltage, and at omega t is equal to beta, both the output voltage 0 and the negative half cycle will be available across the SCR, corresponding that SCR goes to the off state. If the SCR is in the off state, then see here the voltage across the SCR is from alpha to beta, it is in the on state, hence why the output voltage is 0 or voltage across the thyristor is 0, and from beta to here we have the voltage across the thyristor. And see here, if you have the RLE load, then whenever the SCR will be in the off state, always you have the back EMF. Hence why, as long as the SCR will be in the off state, simply the back EMF should act as the output voltage. Back EMF will be acts as the output voltage. Hence why, see from this beta to 2 pi plus alpha, we have the output voltage back EMF. Similarly, from 0 to alpha, the output voltage is back EMF. If there is no RLE load, we have only RL load. If the energy stored in the inductor is discharged at beta, then simply output voltage is 0. If we have the back EMF, as long as the SCR will be in the off state, then the back EMF should act as the output voltage. Hence why, from this 0 to alpha and beta to 2 pi plus alpha, the back EMF should act as the output voltage. See here, we will set from this 0 to theta 1, SCR will be in the reverse biasing mode, and from theta 1 to alpha, forward biasing mode. Observe here, voltage across the thyristor, see here, from 0 to theta 1, SCR will be in the reverse biasing mode, hence we have the negative portion of the voltage across the thyristor, and theta 1 to alpha, small portion, it will be in the forward bias. Hence why you are getting the positive portion across the thyristor, voltage across the thyristor. And from theta 1 to beta, SCR will be in the on state, hence why there is no voltage across the thyristor. And from beta to again 2 pi plus alpha, we have the voltage across the thyristor like this. Here very important. From 0 to theta 1, SCR will be in the reverse biasing mode. Why? Because the back EMF is greater than the source voltage. The resultant voltage across the thyristor will be appears as the reverse biasing voltage. Reverse biasing voltage is nothing but negative voltage. Hence why the negative portion is available from 0 to theta 1, and theta 1 to alpha, SCR will be in the forward bias. Then the voltage across the SCR is simply equal to the source voltage minus back EMF. Hence why these are the output voltage, output current and voltage across the thyristor waveforms. And coming to the derivation, if I want to find out the average DC output voltage, then how can you find out here? See here, average DC output voltage V0 is equals to 1 by 2 pi. Why I am taking the 1 by 2 pi? Here we have for one half cycle you have the source and another half cycle you have the back EMF as the output voltage. Hence why 1 by 2 pi integral. What is the duration of this source voltage? Alpha to beta. Hence why alpha to beta Vm sin omega t d omega t plus what is the duration of this back EMF? E into 2 pi plus alpha, 2 pi plus alpha minus beta. By simplifying this expression, finally you got V0 is equals to 1 by 2 pi into Vm into cos alpha minus cos beta plus E into 2 pi plus alpha minus beta. This is the average DC output voltage of single phase half wave controlled converter with RLE load. So up to now we are discussing the single phase half wave controlled converter with different types of the loads with the R load, RL load and RLE load. If you go through the single phase half wave converter in the output voltage waveform, we are able to collect the single pulse. For completion of one full cycle in the source voltage, we are able to collect the single pulse in the output voltage. Hence why these single phase half wave controlled converters are also called the single pulse converters or one pulse converters. So if you have the output voltage is single pulse, then the order of the harmonics, the frequency of the harmonics will be very low. Okay, if the lower order harmonics are present in the circuit, then the elimination of these lower order harmonics are difficult. Okay, so as much as possible in the output voltage, if you have the more number of pulses, then the order of the frequency of the harmonics are increases. Then the higher order harmonics can be easily eliminated by using the low rating filters. Hence why these single phase half wave converters have only one pulse in the output voltage waveform. Hence why these are called the single pulse converter. If the number of pulses in the output voltage are low like single pulse, then lower order harmonic are available. The elimination of these lower order harmonics are very difficult. Hence why we go with the full wave converters. Okay, we already discussed the classification of the converters. Depends upon the source. The converters are AC to DC converters are mainly classified into two types, single phase converters and the three phase converters. Again, the single phase converters are classified into two types like single phase half wave converters and single phase full wave converters. We are discussed up to single phase half wave controlled converters with the different types of the loads like R load, RL load and RLE load. Now we concentrate on single phase full wave converters. So coming to the single phase full wave converters, again these single phase full wave converters are classified into two types, depends on the circuit configuration or circuit arrangement. Those are single phase full wave midpoint type converters and single phase full wave bridge type converters. Single phase full wave midpoint type controlled converters and single phase full wave bridge type controlled converters. So first we concentrate on single phase full wave midpoint type converter with R load. So coming to the circuit diagram, A circuit consists one isolation transformer whose secondary winding is provided with the center tapping. Here I am taking this R load. Here we have T2, this is T1, and here you have the source. So, coming to the single phase full wave midpoint type converter with the R load, the circuit diagram simply consisting one isolation transformer whose secondary winding is provided with the center tapping, and it consisting two ideal SCRs which are considered as T1 and T2, and the load is connected between center tapping of the secondary winding of the transformer to the common cathodes of the SCR. This is the common cathode point. So between these common cathodes to the midpoint type or center tapping of the secondary winding of this isolation transformer, here we will connect this load, and this is the current flow through the load direction, and here it is the voltage across the load. This is a simple circuit diagram of single phase full wave midpoint type converter with R load. And coming to this operation, first we go with the voltage and current waveforms. So consider the source voltage, coming to this operation of single phase full wave midpoint type converter with R load. So here Coming to this operation, during the positive half cycle of the supply voltage, terminal A is positive and B is negative, and the midpoint with respect to the A it is negative and with respect to the B it is positive. So during this positive half cycle, terminal A is positive and B is negative, corresponding that T1 comes to the forward biasing mode and T2 is in the reverse biasing mode. Why? Because T1 anode and this is cathode, T2 this is the anode and cathode. T1 anode is connected to the positive terminal and T2 anode is connected to the negative terminal. Hence where T1 comes to the forward biasing mode, T2 goes to the reverse biasing mode. So at omega t is equals to alpha, we provide the gate pulse to the first thyristor. At omega t is equal to alpha, we provide the gate pulse to the first thyristor. Hence why the upper half of the source voltage which is available across the T1 is simply transmitted to the load. So the current flow through the circuit is, see here, the current flow through the circuit is given by this A plus, T1, C, R, O minus and like this. So here the current flow through the path is A plus, SCR 1, C, R and the O minus. In this way the current flow through the circuit will be taken place and the total source voltage VA naught is transmitted to the load. Hence why from alpha to pi output voltage simply follows this VA naught. So whatever the voltage is available across the T1 is available as the output voltage. So simply V naught is equals to VA naught. And here you have the resistive load now. Resistive load means voltage and currents are in phase to the each other. So if you go through the current waveform, then this current waveform is simply like this. Here this is the I naught which is equals to V naught by R. Here simply this green line simply represents the I naught which is equals to the V naught by R. I naught is equals to V naught by R. So from alpha to pi T1 will be in the on state. And from 0 to alpha, here we represents the voltage across the thyristor 1 and here we represents the voltage across the thyristor 2. From 0 to alpha, what is the state of T1? T1 will be in the forward biasing mode. So this small portion of the VA naught is available across the T1. From alpha to pi, what is the state of T1? On state. Hence why from alpha to pi there is no voltage across the thyristor. Next, from 0 to pi, what is the state of T2? Reverse biasing mode. So 0 to pi, the T2 in the reverse biasing mode, hence why the negative half cycle will be available across the T2. The negative half cycle will be available across the T2. And similarly, so if you go through this equivalent circuit, so if you represents, simply if you apply the voltage across this loop, if you apply the KVL, to this loop, what you will get here? Minus VA naught plus VT1 plus VT2 plus, you ignore this voltage, these two are in the off state, plus VB naught is equals to 0. Then what you are getting here? VT1 is equals to VT2 is equals to what you are getting here? So here VA naught is equals to minus VB naught is equals to Vm sin omega t, or simply VA naught is equals to minus VB naught. So what you will get here? VA naught is equals to minus VB naught, na? So minus VB naught means Vm sin omega t. So plus VA naught means, so finally here we are getting voltage across the thyristor 2 is minus 2 Vm sin omega t. So what is that meaning? Means whenever the SCR will be in the reverse biasing mode, then the voltage available across this SCR is minus 2 Vm sin omega t, and the maximum voltage is minus 2 Vm. This maximum voltage is simply called the peak inverse voltage. The peak inverse voltage is defined as the maximum voltage available across the SCR in the reverse biasing mode. The maximum voltage available across the SCR in the reverse biasing mode, that is simply called the peak inverse voltage. So the peak inverse voltage in this midpoint type converter is minus 2 Vm. So here during this positive half cycle, these are the output voltage and output current and voltage across the thyristors. And coming to the mode 2, during the negative half cycle, what happens here? During this negative half cycle, terminal A is during this negative half cycle, terminal A is negative and terminal B is positive. Due to that, T2 comes to the forward biasing mode and T1 is in the reverse biasing mode. At omega t is equal to pi plus alpha, we provide the gate pulse to the second thyristor. So from pi plus alpha to 2 pi, the lower half of the source voltage is connected to the load. What is the lower half of the source voltage here? VB naught. See here, this VB naught is transmitted to the load through the thyristor 2 and like this. So this lower half of the source voltage, which is VB naught. So we simply follows the VB naught. So here we already said VA naught is equals to minus VB naught. So VB naught is simply mirror representation of VA naught, then that is the this one VB naught. So what you will write here? or you simply VB naught is equals to minus VA naught, that is minus Vm sin omega t. So what you are getting here, from pi plus alpha to 2 pi, you simply follow the VB naught. What is the pi plus alpha to 2 pi VB naught? This portion. Hence why the output voltage will be like this. Here this output voltage we are able to collect due to the conduction of T2. And if you want to write the current waveform, here we have purely resistive load na, hence why the current is in phase with the voltage, hence why, and the magnitude should depends upon the resistance, hence why we draw the output current waveform like that. And if you go through the voltage across the thyristors from pi to 2 pi, during this negative half cycle of the source voltage, T1 goes to the reverse biasing mode, hence why the negative portion is available, and here the peak inverse voltage is minus 2 Vm. And what about the T2? From pi to pi plus alpha, T2 is in forward bias, hence why small portion of the positive pulse, and pi plus alpha to 2 pi, it is in the on state, hence why there is no voltage across the thyristor. Again you have the positive portion of the source voltage, again T1 forward bias, T2 reverse bias. At 2 pi plus alpha, we provide the gate pulse to the T1, hence why the output voltage again like this, and again here, and output current waveform like this. And from 2 pi to 2 pi plus alpha, T1 is in forward bias, we have some voltage across the thyristor, and 2 pi plus alpha to 3 pi on, and again off. See here, like this. So these are the voltage, output current, and voltage across the thyristors. Okay, very simple operation. During the positive half cycle, T1 is in forward bias, T2 is in reverse bias. Whenever you provide the gate pulse, then T1 comes to the on state. Due to the on state of the T1, the VA naught is available across the load, and during the negative half cycle, T1 is in reverse bias, T2 is in forward bias. If you provide the gate pulse to the second thyristor, then this VB naught is available across the load, and voltage across the thyristor is source voltage. Simply, if T1 is on, then there is no voltage across the T1, you have some output voltage, and we have some voltage across the thyristor too. If T2 is on, there is no voltage across the T2, you have the load voltage, and you have some voltage across the T1. If both the thyristors are in off state, then the output voltage is 0, then you have some voltage across the thyristors like this. So these are the simple output voltage, output current, and voltage across the thyristors. And coming to the average DC output voltage, what you are getting here, V naught is equals to, how many pulses here you have? For completion of one full cycle in the source voltage, you have 2 pulses. This is the one pulse and this is the another pulse. Hence why the output voltage should be written as 2 by 2 pi integral. What is the duration of the pulse? Alpha to pi. So we will write alpha to pi. How much voltage you transfer? Vm sin omega t d omega t. So by simplifying that expression, what you are getting here, V naught is equals to minus Vm. Take Vm by Vm out of the root. So what you are getting here, Vm 2 gets cancelled, Vm by pi integral sin omega t. Integral sin omega t, what you are getting here? Integral sin omega t means minus cos omega t between the limits alpha to pi. So finally you got V naught is equals to Vm by pi into cos 180 is minus 1, minus of minus plus, minus of minus plus alpha. So finally the average DC output voltage is given by V naught is equals to Vm by pi into 1 plus cos alpha. So here what you are getting, V naught is equals to Vm by pi into 1 plus cos alpha. So if alpha equals to 0, if you provide the minimum firing angle, then the maximum output voltage is 2 Vm by pi. If alpha equal to 0, cos 0 1, 1 plus 1 2, 2 Vm by pi. If you consider the firing angle is 180 degrees, if alpha equal to pi, then what is the V naught? Cos pi minus 1, minus 1 plus 1 gets 0, and finally you are getting the output voltage is 0. So here the output voltage will be controlled from 0 to 2 Vm by pi by controlling the firing angle from 180 to 0. If you keep the minimum firing angle alpha equal to 0, then you are getting the maximum output voltage, which is 2 Vm by pi. If you keep alpha equal to 180 degrees, then you are getting the minimum output voltage, which is V naught is equals to 0. And if you want to find out the RMS output voltage, Vrms is equals to how many pulses you are getting per completion of one full cycle? 2 pulses. So 2 by 2 pi integral, what is the duration of the pulse? Alpha to pi Vm square sin square omega t d omega t whole power 1 by 2. By simplifying this expression, you are able to find out the RMS output voltage. So how can you simplify this expression? Vm square whole power 1 by 2, take out of that whole power 1 by 2, we will write Vm, 2 gets cancelled, 1 by pi integral alpha to pi. This sin square omega t is written as 1 minus cos 2 omega by 2 d omega t whole power 1 by 2. So by simplifying this expression, what you were getting? Vrms is equals to, right, Vm into 1 by pi into 2. Here 1 into omega t means omega t between the limits alpha to pi minus sin 2 omega t by 2 between the limits alpha to pi whole power 1 by 2. By simplifying this, Vm into 1 by 2 pi into pi minus alpha minus sin 2 pi 0 plus sin 2 alpha by 2. So finally Vrms is equals to Vm into pi minus alpha by 2 pi plus sin 2 alpha by 4 pi whole power 1 by 2. That is a simple RMS output voltage. And finally you want to find out the average DC output current. I naught is equals to V naught by R and IRMS is equals to Vrms by R. So these are simply RMS output voltage, and this is the average DC output voltage. V naught equal to Vm by pi into 1 plus cos alpha. So this is simple single phase full wave converter with R load. Next we go with the single phase full wave midpoint type converter with RL load. Single phase full wave midpoint type converter with RL load. Coming to the circuit diagram, Coming to the single phase full wave midpoint type converter with R load. Coming to this operation, during the positive half cycle of the supply, here it is the VI naught and it is the VB naught. So during the positive half cycle of the source voltage, terminal A is positive and B is negative. Corresponding that T1 comes to the forward biasing mode, T2 is in the reverse biasing mode. At omega T is equal to alpha, we provide the gate pulse to the first thyristor. Then T1 comes to the on state. So if the T1 is in the on state, this VA naught is transmitted to the load. So from this alpha to pi, the source voltage VA naught is available across the load. Hence why you simply follows VA naught due to the conduction of T1 from alpha to pi. And here we have the resistive load and the inductive load. This is the I naught and this is the V naught. So if you go through this RL load, depends on the value of the inductor, the circuit should operate in two modes. First one is continuous conduction mode. Continuous conduction mode, which is collecting for high value of the inductor. And second one, discontinuous conduction mode, which is collected for low value of the inductor. If the inductor in the load is high, then you are getting the continuous conduction mode. If the inductor value in the load is low, then we are getting the discontinuous conduction mode. So assume large value of the inductor or high value of the inductor, then simply we go with the continuous conduction mode. So from alpha to pi, T1 will be in the on state. Hence with this total VA naught is available across the load and current flow through the circuit is A plus, T1, C, R, L and A plus. Due to that, there was some energy must be stored in the inductor. So the energy stored in the inductor is like this, from alpha to pi. So assume large value of the inductor, then the converter is operates in continuous conduction mode. What is the meaning of continuous conduction mode? Means at which the instant the next SCR come to the, up to that the present SCR is in the on state. For example, next incoming SCR, what is the next incoming SCR? At pi plus alpha, we are going to fire the second SCR. So at pi plus alpha, this SCR2 is called incoming SCR and SCR1 is called outgoing SCR. So if you go through the continuous conduction mode, due to the presence of the inductor, the energy stored in the inductor is used to maintain the on state of the outgoing SCR is continuously till the incoming SCR. That means, see, at omega T is equal to pi, even though the output voltage is 0, the output current cannot be 0. Due to that, the energy stored in the inductor is discharges to the source through the same thyristor. Hence why the energy stored in the inductor will be discharged like this. So up to pi plus alpha, you assume the energy stored in the inductor is discharges. Hence why the conduction period of the T1 is extends up to the pi plus alpha. So up to pi plus alpha, T1 will be in the on state. If T1 is in the on state, then this small portion of the negative source voltage is available across the T1. Hence why the negative portion is available across the load. So here from alpha to this pi plus alpha, here from alpha to pi you have the positive output voltage, positive portion in the output voltage waveform that represents some power should be transmitted from source to the load. From pi to pi plus alpha, we have negative portion in the output voltage waveform. That negative portion simply represents some power should be transmitted from load to the source. And during this negative half cycle, again terminal A is negative and B is positive, corresponding that T2 forward bias, T1 reverse bias at omega T is equal to pi plus alpha. We provide the gate pulse to the second thyristor. See, from pi plus alpha to 2 pi, this VB naught is available across the load, and again the output voltage simply follows the VB naught from pi plus alpha to 2 pi due to the conduction of T2. And again here there was some energy must be stored in the inductor, and again it is discharges. Due to that, some negative portion of the output voltage is available across the load like VB naught, and again T1 on, again you have the output voltage and negative portion, and again here T1 and again here T2. Similarly from 0 to alpha also T2 will be in the on state, hence why the discharging can will be taken place. And coming to the voltage across the thyristors, from 0 to alpha, what is the state of T1? Forward bias, hence why this small portion of the positive voltage is available across the T1. Alpha to pi plus alpha, what is the state of T1? On state, hence why there is no voltage across the T1. From pi plus alpha to 2 pi plus alpha, what is the state of T1? Off state. So from this pi plus alpha to 2 pi and 2 pi to 2 pi plus alpha, and again 2 pi plus alpha to this one on, and again like this. That is the simple voltage across the T1. So if you want to draw the voltage across the T2 from 0 to alpha, reverse biasing mode, simply have the negative portion, and pi to pi plus alpha positive portion, pi plus alpha to 2 pi plus alpha 0, again negative portion, like that. That is the simple voltage across the SCR2. So these are the simple output voltage, output current and voltage across the thyristors. So if we go through this single phase full wave midpoint type converter with RL load under continuous conduction mode, these are the output voltage and output current waveforms. And if you want to find out the average DC output voltage, what you are getting here, average DC output voltage, V naught is equals to, how many pulses you are generating for completion of one full cycle? This is 1 and this is 2. 2 pulses will be generated. What is the duration of the pulse? From alpha to pi plus alpha. Then you write average DC output voltage like 2 by 2 pi integral alpha to pi plus alpha. How much voltage you transmitted? Simply source Vm sin omega t d omega t. By simplifying this expression, what you are getting, take Vm and minus cos omega t between the limits alpha to pi plus alpha. 2 gets cancelled, so Vm by pi. So finally Vm by pi, you replace the limits, minus cos pi plus alpha, minus of minus plus cos alpha. Cos 180 plus theta minus alpha, so minus of minus plus, so finally V naught is equals to 2 Vm by pi cos alpha. It's very very important. The average DC output voltage of single phase full wave midpoint type converter with RL load in continuous conduction mode especially is simply given by V naught is equals to 2 Vm by pi cos alpha. If you go through this, if alpha equals to 0, what is that average DC output voltage? Simply 2 Vm by pi. If alpha equals to 90, V naught is equals to 0. If alpha equals to 180, then this V naught is equals to minus 2 Vm by pi. Minus 2 Vm by pi. So if you observe this variation of the voltage, output voltage with respect to this firing angle, if it is 90, then you are getting the maximum positive voltage, which is 2 Vm by pi. If it is 180, then you are getting the maximum negative output voltage, which is minus 2 Vm by pi. So if you vary the firing angle from this 0 to 180, then that output voltage should be varies like this. And what is that meaning here? If you observe this quadrant representation, always the current is positive. Why? Because always the current flow through the load in this direction only. Either T1 on or T2 on, the current flow through the load is from right to left. But depends on the firing angle, the output voltage may be positive or negative. So if you have the firing angle lies between 0 to 90 degrees, then we are able to collect the first quadrant operation. And if alpha lies between 90 to 180, then you are able to collect the fourth quadrant operation. Here what is the meaning of the first quadrant and the fourth quadrant means? If you go through this first quadrant, here we are able to collect rectification, and if you go through this fourth quadrant, we are able to collect inversion. So what is that meaning means? If you go through the single phase full wave midpoint type converter with RL load, if alpha is less than 90 degrees, then we are able to operate that converter as the rectifier, and we are able to collect the rectification operation. For the same single phase full wave midpoint type converter with RL load and in the continuous conduction mode, if you maintain alpha greater than 90 degrees, that is alpha lies between 90 to 180, then that converter should act as the inverter and the inversion operation should be taken place. That is the meaning. Hence why this single phase full wave midpoint type converter is simply called the 2-pulse converter. Why? Because for completion of the one full cycle in the source voltage, we are able to generate the 2 pulses in the output voltage waveform. Hence why this is simply called the 2-pulse converter. And if you go through this continuous conduction mode, what is the conduction of each SCR? For example, T1 conducts from alpha to pi plus alpha. Alpha to pi plus alpha means that SCR conducts for 180 degrees. So if you go through this continuous conduction mode, in continuous conduction mode, the conduction angle is 180 degrees. Very, very important. Gamma means conduction angle. That in continuous conduction mode, the conduction angle gamma is equals to 180 degrees. And if you go through the discontinuous conduction mode, then that conduction angle is less than 180 degrees. Later we discuss discontinuous conduction mode. First we concentrate on continuous conduction mode. These are the output voltage and output current waveforms in continuous conduction mode. And assume here you are getting here alpha less than 90 degrees. If you take alpha less than 90 degrees, then these are the voltage and current waveforms. So if we alpha less than 90 degrees, how the converter should be operates? Simply this converter should act like rectifier. What is that meaning means? See here in the output voltage waveform, from alpha to pi, some power should be transmitted from source to the load, which is considered as the P1. And this negative portion of the output voltage simply represents the energy stored in the inductor is transmitted to the source. That means some energy is transmitted from load to the source. Then that is considered as the P2. Then what is the resultant power here? P1 greater than P2. Then some power should be transmitted from source to the load. Hence why rectification is done. If P2 dominates the P1, then some power should be transmitted from load to the source. What is the load here? DC. What is the source? AC. DC to AC. Hence why inversion operation should be taken place, and that converter should access the inverter. If that converter is operated by the AC voltage, AC source, and the inversion operation should be taken place, that type of converter is called line commutated inverter. The type of converter is called line commutated inverter. Line commutated inverter means even though the circuit is energized by the AC, the inversion operation should be taken place. Inversion operation means simply depends on the value of the inductor. If alpha is greater than 90 degrees, then some power should be transmitted from load to the source. Here these are the output voltage and output current waveforms for rectification operation. For the same converter, if you want to represent the inversion operation, then we will see the current waveforms and voltage waveforms. So if you go through this, alpha greater than 90 degrees, then so coming to this operation for alpha greater than 90 degrees, see here, at omega t is equal to alpha, which is greater than 90, we provide the gate pulse to the first thyristor. Hence why from alpha to pi plus alpha, T1 will be in the on state, and from pi plus alpha to 2 pi plus alpha, T2 will be in the on state, and 0 to alpha, T2. So what observe here? From 0 to alpha, in the output voltage you have the negative portion. That means some power should be transmitted from load to the source. And from alpha to pi, positive output voltage, some power should be transmitted from source to the load. See, from alpha to pi, the power should be transmitted from source to the load is taken as P1, and from pi to pi plus alpha, the power should be transmitted from load to the source P2. Here P2 dominates the P1. Hence why the resultant power should be transmitted from load to the source. Hence why the converter should act as the inverter. The converter should act as the inverter. So if you go through the single phase full wave midpoint type converter with RL load, depends on the value of the inductor, we are able to collect either rectification or inversion. If the inversion operation should be collected from that converter, that is simply called the line commutated inverter. And these are the line commutated inverter output voltage, current waveform and voltage across the thyristor. And derivation should be same. Okay, derivation should be same. Whether it is a rectifier or converter, whether it is in the inversion operation or rectification operation, the average DC output voltage V0 equal to 2 Vm by pi cos alpha. If the rectification is operation should be taken place, output voltage is in positive magnitude 0 to 2 Vm by pi. If inversion operation should be taken place, then this V0 becomes negative. Depends upon the value of alpha, it varies from 0 to minus 2 Vm by pi. Hence why here we are able to collect the first quadrant operation and the fourth quadrant operation. Hence why the single phase full wave converter with RL load is simply used to collect two quadrant operation at a time, either first quadrant operation or fourth quadrant operation. And coming to the RMS output voltage, simply Vrms is equals to how many pulses you are generating? 2 pulses for completion of one full cycle, and the duration of the each pulse is alpha to pi plus alpha Vm square sin square omega t d omega t whole power 1 by 2. So by simplifying this, take Vm square out of the 1 by 2 and 2 gets cancelled, 1 by pi integral alpha to pi plus alpha, this sin square omega t written as 1 minus cos 2 omega t by 2 d omega t whole power 1 by 2. So by simplifying this, Vm into 1 by pi integral 1 into omega t, take 2 outside, so 1 by 2 pi omega t between the limits alpha to pi plus alpha minus sin 2 omega t by 2 between the limits alpha to pi plus alpha whole power 1 by 2. What happens here by simplifying this, Vm into 1 by 2 pi into here pi plus alpha minus sin 2 pi plus 2 alpha minus of minus plus sin 2 alpha by 2 whole power 1 by 2. What is sin 360 plus theta? Sin theta. So here we are getting minus sin 2 alpha plus sin 2 alpha gets cancelled, alpha gets cancelled and pi gets cancelled. So finally Vrms is equals to Vm by root 2, that is equals to Vs. This is the RMS output voltage of single phase full wave midpoint type converter with RL load. So in this class we just discussed the operation of single phase half wave converter with RLE load and single phase full wave midpoint type converters with R load and RL load. Thank you.